In this next video, we'll talk about work, energy, and power, Unit 3 again. But this time, we're going to talk about work. So what is work, and how does it work do things? How does it change the system? All that fun stuff. Learning targets are, I know what work is, and I can calculate the work done by a force. So when we talk about work, maybe a lot of different words come, or a lot of different definitions come to mind when we think of work, whether you have a job, or you go to work, or you do work while you're at work, or all kinds of definitions that we have in our everyday words. But in physics, work is a very specific thing. Work is the product of force times distance. And we know that force is a vector, and we know that displacement or distance is also a vector. And so what we get is that work is equal to force times distance times cosine theta. So this cosine theta thing comes in because these are vectors and we have to think about some important stuff. So first of all, when we talk about work, work is what a force does, or work is what happens when a force is exerted over some distance. Work is a really important concept in physics, and we use it a lot because it's very useful, it's very easy to deal with, and it makes a lot of sense when you think about it. But getting into it, it might be kind of daunting, kind of difficult. So let's talk about what work is and how we calculate it first. All right, if a force is parallel to a displacement, then it will do work. So work is only done by forces that are parallel to the displacement. So if a force is exerted and it's perpendicular or normal to a displacement, then it won't do any work at all. For instance, if I were to push up on an object while it was moving side to side, and so our displacement vector is this way, and our force vector, my force vector that I'm pushing is upwards, then these are perpendicular to each other, and so no work will be done, because there's no component of that force vector that's parallel to the displacement vector. When I think about it, I can draw maybe a triangle that would say, here's my force vector, and here's my displacement vector. Or maybe let's not call it our displacement vector. Let's call it the x component of our force vector. And there's our y component, Fy. And this is the angle, theta. If my displacement vector is horizontal to the right in the positive x direction, then I would say that my x component of this force is going to be parallel to that displacement vector. Sure, you should be able to see that from the diagram. But if I think about this leg of the triangle is the adjacent leg, right? So it would be Fx is equal to the force times cosine of theta. And I said earlier that a work is force times displacement. So the force that actually does work is F cosine theta. And if I multiply those together, I get F times cosine theta times my displacement is my work. Or to write it more succinctly, I guess, it's F d cosine theta. We have to be careful about this theta here. Sometimes we're given inclined angles or inclined planes, and that's not what we're talking about when we talk about this angle theta. When we talk about this angle theta, we're saying that there's some force vector, maybe it's out in this direction, and some displacement vector, maybe it's at this direction. And the angle between these two vectors, that is the angle we want to talk about. Sometimes an inclined plane's angle will be the same as that angle between those two vectors, but not always. So we have to be very, 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 very careful when we do our analysis, especially when we're talking about inclined plane stuff. When we talk about something like say a box, and here's a box, it's on a horizontal surface, and you pull up on it, some angle theta, and you exert maybe a tension force onto a rope, and that tension force causes the mass to accelerate and move in this direction. then we'd say that the angle between t and our displacement vector is going to be this theta angle here. But let's say we're on an inclined plane and I pull up with some angle theta. And that's my tension vector. And this is my angle of incline. And maybe I'll call it something else. We'll call it phi, the Greek letter phi instead of theta. So this is a different angle here. This is completely different from this angle here with our tension. And so if our displacement is up the inclined plane, then our work done is still going to be tension times d times cosine of theta. And this angle of incline isn't going to have anything to do with our equation for work, right? Because the displacement is along that same is parallel to the surface. Our tension vector is exerted, that is some angle theta from that surface, and so the angle of incline doesn't really matter. It will matter if we have to deal with friction and things like that, but it'll show up through the force of gravity when we talk about the normal force and everything. Because if you remember, our friction force is equal to mu k times n, and if we're on an inclined plane, then we get mu k times m times g times the cosine of phi, where phi is the angle of incline. So if we have friction and we're talking about work done by friction, then that angle will show up. But most cases, this angle theta is very different from the angle of incline. So be aware of that. If we wanted to calculate work done, this is how we would do it. We'd figure out the magnitude of the force F. We would figure out the distance that force acted for. We could figure out the angle between those two vectors, and then we could just plug it into a calculator FD cosine theta. Pretty straightforward stuff. So when I talk about work is a scalar. Work does not have a direction to it. Work can be negative, but it doesn't mean it's pointing in the negative x direction or the negative y direction. It usually means that we're slowing something down or we're removing energy. So if work is negative, we are removing energy from the system. If work is positive, we are adding energy to a system. And don't worry about this energy stuff just yet. We'll talk about that in the next video, what energy is, and we'll talk about how work and energy are related through the work kinetic energy theorem and the work energy theorem. But for now, just know that work being negative means that work is being done on the system, and work being negative means work is being done by the system on the surroundings, and work being positive means that work is being done to the system. So usually it means that the system is increasing in velocity. Work is positive. If the system is slowing down, then we're removing kinetic energy, and so work would be negative for that. If you look at the equation for work, it says work is equal to force times displacement times cosine theta. Cosine theta doesn't have any units associated with it, but force and distance do. If you recall from last unit, our units of force are newtons, and units of displacement or distance, those are meters, right? And maybe from further back, we talked about how a newton is a kilogram times a meter over a second squared, or a mass times an acceleration, right? Acceleration and mass. But then we multiply it by this other meter, and what we get is a kilogram, a meter squared, divided by a second squared. This thing here is called a joule, and it's given the letter capital J, or joule. So the units of work are joules, and we'll see that the units of energy are also joules. If I have this cosine theta thing happening, and I can see that maybe, or maybe you remember from trig or from some other place, that there's a range that cosine theta can have. Cosine theta can be at most negative, or at least -1, and at most it can be +1. And it happens to be that when I am positive 1, that's when cosine of theta, well, theta has to be 0 for me to be equal to 1. And then theta has to be 180 degrees for me to get a negative 1 out. So if I think about it, I could say something like if the angle between the force and the displacement vector theta, if theta is, or I should say if theta is between negative 90 degrees and positive 90 degrees, but not equal to either of those, then the work will be positive. If our angle is between positive 90 degrees, but less than negative 90 degrees, then our work will be negative. And finally, if the angle theta is equal to plus or minus 90 degrees, then work is 0. That's where we have all of our force that is perpendicular to the displacement, and so none of that force can do work because none of it is parallel to the displacement. The work will be 0 if plus or minus 90 degrees. So if I want to kind of draw a picture or something to explain that, let's say I'll draw, coordinate system. Here's my XY coordinate system. And my force, if I exert a force this direction, and my displacement will always keep the displacement on the x-axis. But if my displacement is along the x-axis, this angle theta here, this is between 0 and 90 degrees. And if I do plug this angle into cosine, I will get a positive value. If my angle for F2 is between 0 and negative 90 degrees, and I plug that in, I will get a positive value out, right? Because cosine of negative 50 degrees is the same thing as cosine of 50 degrees, and those are both positive numbers. Cosine of 60 degrees, cosine of negative 60 degrees, same number, both of them are positive. And so this is what we have when we have a positive work being done. Similar situation, here's my x and my y axes. My displacement is still along the x-axis. But if I were to point my vector over here, or my vector down over here, my force vector, F1, F2, you can see that this is greater than 90 degrees. And this is greater than negative 90 degrees. And so both of these would do a negative work. Positive work there, negative work there, and that's what we should see for most cases. Final thing that we should talk about is, again, if our displacement is along the x-axis and our force F1 is up or directly down, that's plus or minus 90 degrees. And so those will give us 0 work. I'm going to put a couple of vectors up here, and we'll see if you can determine whether or not they will do positive or negative work. So for the first one, here's our force F and our displacement D. Second one, we will do, here's our force F, and here's our displacement D. Third one, here is our displacement D, and here is our force F. Fourth one, here is our force F and our displacement D. Fifth one, here is F, here is displacement, and finally, here's our force F, and here is our displacement D. So take a moment, pause the video if you want, and try to figure out if these will do positive work or negative work, given the angle between the two vectors. Okay, so hopefully you got that done. Here are your answers. For the first one, we have F and D, the angle between them is 0 degrees, and so this would be positive work. For B, the angle here is less than 90 degrees, and so this would be positive work. The angle between force and displacement on C, that is 180 degrees, so these are anti-parallel to each other, so the work will be negative. Here again, we have F and D. The angle is greater than 90 degrees. It sits in the negative range of the axes. If I were to draw a coordinate axis there, X and Y. So my X will be negative. Since D is entirely along the X axis and it's entirely positive, we could see that the work is negative for that one. Here, our work is going to be 0 because they are 90 degrees perpendicular from each other. And finally, our last one, F, also a 90 degree angle, even though this isn't our regular coordinate axis. Maybe it's rotated to point along an inclined plane or something, but it's still a force and displacement vector there, 90 degrees from each other, and so they will do no work whatsoever. So let's go back and talk more about the equation for work, which says work is equal to F times D times cosine theta. So if you were to be given a force, let's say maybe a push force, is 50 newtons, and it's exerted over a displacement of 0.5 meters. And the angle, maybe the push force is horizontal and the displacement is also horizontal, and so the angle between those two vectors is 0. If I wanted to calculate how much work this force will do, I would just simply put in my force amount, 50 newtons, times my displacement amount, 0.5 meters, my cosine of theta, which is 0 degrees, because we know cosine of 0 degrees becomes 1, and so we just get 50 times 0.5, which is 25 newtons times meters, or 25 joules, and that would be our answer, 25 joules. Try another one. Let's say we do a force that is gravity. So gravity is acting and it's pulling maybe a ball down. So we've done a projectile motion problem. The ball has reached the maximum height, and so its velocity is 0 at the top. But force of gravity is going to start pulling it down and causing it to accelerate downwards. So force of gravity, we'll say, is going to be acting, and it's m times g. My displacement, we'll say, is 1 meter. And also the mass of this ball is 100 grams, or 0.100 meters. So if I want to calculate the work done by gravity, I would do work is equal to force times distance times cosine of theta. So we can think, this is a ball. Here's our maybe a free body diagram. And the only force acting it is gravity. And we know that it's going to move down. So our displacement will point down. The angle between force of gravity and the displacement then is still 0 degrees, right? They're still parallel to each other. And so we would get cosine of 0 degrees is just 1. My force, however, I don't really know what that is directly, but I do know its mass, or I do know the mass. I do know g, so I can calculate it as F sub g times displacement. My F sub g, that's mass times gravity, times my displacement. And then I can plug in some numbers. So my mass is 0.100 kilograms. My g value is 10 meters per second squared, and my displacement was 1.0 meters. And so if I do 10 times 0.1, that's 1. So then 1 times 1 is just 1, and the total work done would be 1 joule. We'll try one more. Let's say there's a friction force. So we pushed a box, we've got it going, and then we let go. We stop pushing this box. The coefficient of friction between the box and the floor, we'll say, is 0.3. We'll say the mass of the box is 10 kilograms, and this is on a horizontal surface. And we'll say it's 1.0 meters long, so that's our displacement. Now I want to calculate the work done by friction while this thing slides to rest over this 1 meter distance. So the work done, is equal to force times distance times cosine theta. My force is the friction force, so I'll replace my F with F sub k, my displacement is d, and my cosine is theta. Now we should be careful about this because when we talk about forces and displacements, they always had a direction, and so the negative sign mattered. Here, when we talk about work, we're talking about a scalar, and so the direction does not matter. I know that work can be negative sometimes, but that negative sign will always come from your angle, from cosine theta. But it will never come from your force, and it will never come from your displacement. So when you think about this equation, work is force times distance, think of it as the absolute value of force times the absolute value of displacement times cosine theta. Theta will give you a negative or a positive. F and D should not. So friction force here, when we calculate it, is going to be a positive value that we plug in. And displacement, no matter what direction it is also going to be a positive value. We know the equation for friction is going to be mu k times the normal force. And so we get mu k times n times d times cosine theta. So at this point, we got to think, what is our normal force? Well, we're on a horizontal surface, so I know my normal force has to equal my force of gravity. Since there's no other objects on top of this box, nothing else pulling it down, no other forces acting up and down, just that friction force. And so we'll have force of gravity is equal to normal force. So N is equal to mg. So I can plug that in for my normal force, and I get mu k times n, which is mg, times my displacement, times cosine of theta. Our friction force is going to point backwards in the left, and our displacement should be to the right. So that means that our angle between these two vectors is 180 degrees. So my theta is 180 degrees. That's what gives us the negative work done by friction, not the fact that friction is a negative value. So I can plug in 0.3 for mu. My mass was 10 kilograms. G is 10 meters per second squared. My displacement is 1.0 meters. And then I'll have cosine of the angle 180 degrees. So cosine of 180 degrees, that's just minus 1. So I get is a negative, and I get 10 times 10 times 1, that's 100, times 0.3, so that would be 30. And my units are kilograms times meters per second squared times meters, which is a joule. So 30 joules is our answer. I'll give you a shot to try to calculate the work done by a force or two. We'll go ahead and slide over to the next page. And so we'll say that we have a force, a push force that does work horizontally. And this push force is parallel to our displacement. So the push force of 100 newtons and the displacement will be 5 meters. So go ahead, also angle theta is 0 degrees. These are parallel to each other. So go ahead, take a second, try to calculate the work done by this push force. Right, not too terrible. We know that work is equal to force times displacement times cosine theta. We know our theta is 0, so our answer for cosine theta is 1. And we can just call this work is equal to F times D. So force is 100 newtons, D is 5 meters. We get 500 newtons times meters, which is 500 joules. Try another problem here. Let's say that we have a spring force that's exerted for a distance of 0.25 meters or 25 centimeters. The K constant for the spring we'll say is 100 newtons per meter. And our stretch distance, delta x, is going to be equal to that 0.25 meters. So we start off, maybe we've stretched this thing 0.25 meters, and we want to know how much work will this spring do as it pulls this mass from the maximum stretch distance all the way back to the natural length of the spring. So I'll give you a couple moments, try to work through that and see if you can come up with an answer. All right, so you might have come up with an answer. You'd say it's probably something like 25 or maybe 25 times 0.25. I don't know. Let's work through it. So work is equal to force times displacement times cosine of theta. And let's think about the angle that we're going to work with. Our displacement, since we're starting off as a spring completely extended, draw a picture of that. So spring completely extended. The distance between the natural length of the spring and the final stretch length is 0.25 meters. When we let go of this mass, we can think the displacement, the direction that's going to go is this way. And the spring force is going to be pulling it that way as well. And so the angle between these two objects, or these two vectors, is 0. So theta is equal to 0 degrees. Which means cosine theta, cosine of 0 degrees, is going to be 1. And so our force is just going to be equal to K times X times displacement, which is X. So I get Kx squared is my answer. And if I plug in my values, 100 newtons per meter times x squared, so 0.25 meters squared, I will get 25, oh no, 6.25 joules. But this is wrong. The reason why it's wrong is because the spring through Newton's third law is going to exert a force on the mass, but it's also going to exert a force on the wall in this direction. And so the spring force is going to be, or the force that the mass experiences is going to be 1/2 of the spring force. And so the equation we should get is actually 1/2 kx times x, or 1/2 kx squared. And so this value we got is too big. It's actually twice as big. So let's go ahead and do that the correct way. Work is equal to the force that's exerted on the object, which is 1/2 kx times x, which is 1/2 kx squared, or 1/2 times 100 newtons per meter times 0.25 meters quantity squared. If I do that, I get 3.125 joules, and that is the answer that we should get. So when it comes to spring forces, they're a little weird. They have a 1/2 on them. And when we get to the energy discussion and stuff like that, when we talk about spring energy, we'll see why that 1/2 comes about. But for now, that's how we calculate work. It's force times displacement times cosine of the angle between the force and displacement vectors. So one more time, work is F d cosine theta. Work is a scalar. It does not have direction. Positive means we're increasing velocity or increasing energy of a system. Negative means we are decreasing the energy of a system. And one more thing, only parallel forces do work. So only forces that are parallel to the displacement will actually do work. So with that said, that's it for work. I think we have another couple videos coming up for energy and stuff, and also conservation of energy, and so stay tuned for those. We will see you later.